Welcome to the board. In this board, we will discuss image segmentation. Image segmentation. So, what is meant by segmentation? Segmentation means we are dividing into segments. Suppose this is an image. We are dividing this in this way. We are partitioning this image. Okay. Then the a part of the image which we divided is called the segmentation. So now how to do image segmentation? So to do image segmentation, we need to know some fundamentals. What are those fundamentals? Up to now we used for the transformations, Fourier transformations and integrals, and after that we used set theory. And now we will use first first order derivatives, means differential equations. We use differential equations. So for the differential equations, first order derivative, second order derivative and so on, we need some fundamentals. What are those fundamentals? See here, R represent the entire spatial region occupied by an image. So suppose this is an image which is occupied the spatial region, then this is the spatial region. This image is occupied within this spatial region, that is representing with the R. Image segmentation is a process that partitions R into n subregions. So we are partitioning this region into n subregions. So the region is represented with R. So the subregions are represented n subregions, R1, R2, R3 and so on n. Then it should be union of I is equal to 1 to n, Ri is equivalent to R. This is one fundamental rule. Means the union of all these regions is equivalent to R. We know this. We are clear for this. Whenever we divided a region, then combine all those parts. Then again we will get the same region. That is the union. Then Ri is a connected set. I is equal to 1 to n. Yes, Ri means we dividing a region here. Suppose R3. That R3 is also connected to this region only. So this is the rule. And after that, Ri intersection Rj is equivalent to 5, which means null. Means Ri intersection Rj. So suppose here this is one, this is Ri, this is Rj. The intersection points of these two is null, is 5. This is another rule. Negation of Ri is equivalent to true. For I is equal to 1 to n. Always Ri is equivalent to true. And union of Ri and Rj is equivalent to false. The intersection of these. For any adjacent regions Ri and Rj. So suppose these two are adjacent regions, then the boundaries of these two, the boundary of this Ri and the boundary of this Rj are different. We cannot get a union of these two because boundaries are different. We are partitioning the boundaries. That's why Ri union Rj is equivalent to false. These are the fundamentals. Now we will see an example application. See, image containing a region. So in this region, this is the image. So this image containing a region of constant intensities, or the image is filled with constant intensity values. Then image shown boundary of the image region. So this is the boundary of the image region, inner region, and we are obtaining from intensity discontinuous. Okay, then result of segmentation, the image in two regions is this one. So this is one region, this is another region. So the image differentiation segmentation is represented by the white color, another color. Then image containing a textured region. So the image is contained a textured region. Then result of edge computation, the large number of small edges that are connected to the original boundary, making it difficult to find a unique boundary using only edge information. Then the result of segmentation based on region property is this one. So in this way we will segment the image. Now to do these kind of segment operations, we need a background of first order derivative, second order derivative. I already told you differential equations are, we are using differential equations. So first order derivative is represented as dou f by dou x, means f is our image representation, and with respect to x coordinate. So dou f by dou x is the first order derivative representation, is equivalent to, we can also write it as first order derivative f of x. So the expression first order derivative is given as f of x plus 1 minus f of x. This is the expression for first order derivative. The second order derivative means the one first order derivative into another first order derivative, which means dou square of by dou x square, which is multiply this with again this, then square of it, which results the expression f of x plus 1 plus f of x minus 1 minus 2 f of x. This is the second order derivative. This is the background equation representations. Then see an example. See here, this is the image. A horizontal intensity profile through the center of the image, including isolated points, all isolated points, noise points, is the result of this one. Then the simplified profile, which is containing the points joined by dashed lines, also given here for clarity. So the image strip corresponds to the intensity profile, and the numbers in the boxes are the intensity values of the dots shown in the profile. The derivatives were obtained by using the first order derivative and the second order derivative. All these obtained from the first order derivative. All these obtained from the second order derivative. The intensity strip values are represented by this intensity graph with the ramp isolated points, by taking all these all these considerations, by these calculations. These are the outputs. Now see some characteristics of first order derivative and second order derivatives. So where we use first order derivative and where we use second order derivative, what are the applications? So first order derivative generally produce thicker edges in image. So whenever we want to segment, extract thicker edges, whenever we want to produce thicker edges in an image, you can apply first order derivative. And second order derivatives have a stronger response to fine detail such as thin lines, isolated points, and noise. So, whenever we need a stronger response to fine details, means whenever we need thin lines, details, isolated point details, noise details, there we can apply second order derivatives. The second order derivatives can give thin line information, isolated points information, noise information. A fine details it can give. And second order derivative produce a double-edged response at ramp and step transition in intensity. At ramp and edge, the double-edged response, we can get a transition in intensity we can get from the second order derivative. The sign of the second derivative can be used to determine whether a transition into an edge is from light to dark or dark to light. So whenever we use a sign of second order derivative, then we can determine the transition into edges from light to dark, from dark to light. The transition we can observe, we can get. For that also the second order derivative is useful. To do all these we need some edge detections. So to do edge detections, detection of isolated points, we using detection of isolated points by using Laplacian. Laplacian formula we already seen. Delta square of f of x comma y is equivalent to delta square of dou square of f by dou x square plus dou square of f by dou y square, which is the expression of, I already explained this in the previous lectures, f of x plus 1 comma y, f of x minus 1 comma y, f of x comma y plus 1, f of x comma y minus 1 minus f of 4 into f of x comma y. And the g of x comma y is 1 if r of x comma y is greater than or equal to t. Otherwise, it is 0. And how to do, what is the example and application for line detection? In this example, see, this is the point detection. Okay, this is the point detection Laplacian mask. And this is the X-ray image of turbine blade. It is a turbine blade with a porosity contains a single black pixel. This is the pixel. Okay, so now we have to extract this one and find out this one, point out this one. Then the result of convolving the mask with this image, this mask with this image, this is the Laplacian point detection mask, then this is the resultant image. And from this we are using the equation which we have seen before, is showing the single point and which is enlarged and identified easily. Then this is the output we got from the Laplacian point detection. Now, see another detection from the image, which is line detection. How to detect a line? Suppose this line. Okay. Then for this, we are using second derivatives to result a stronger response and to produce thinner lines than first derivatives. So the second order derivatives, we already seen the equation for the second order derivative, dou square x y by dou x square, which is giving and producing the stronger response of thinner lines, which is giving the thinner lines. So to do this, we have to double line effect of the second derivative must be handled properly. This double line effect of the second order derivative we have to handle properly. I'll show an example for line detection, how to detect a line. See this example. In this example, this is the original image. Okay, from this image, upon this image, a Laplacian image, which is a magnified section obtained by the positive or negative double line effect characteristic of the Laplacian, giving this result. This is the result after applying Laplacian double line effect characteristic, and then absolute values of the Laplace giving the result of image like this. Absolute values, all the lines are detected, absolute lines, and the positive values of the Laplacian. So here a negative or positive values are involved here also. Only positive values of the Laplacian giving the line detections up within this image. In this way, the output of the line detections of the image we can identify and extract. And now detecting line in a specified direction. In a specified direction, suppose, then how to detect? For that, suppose we are taking R1, R2, R3 and R4, these are denoting responses of the masks. Okay, so for this image, this is the mask. For this is the mask in this way. Okay, then at a given point in the image, Rk greater than Rj, for all j not equal to k, then that point is said to be more likely associated with the line in the direction of mask k. So so in this example, to detect, to find the horizontal line, we have to use this mask. For the plus 45 degrees, we have to use this mask. And for the vertical line detection, we applying this mask. And for the negative 45 degrees line detection on that within that angle, we will use this mask. So all the line detection masks and angles and axes are showing within the mask. And by this, I'll show an example. See this example. So in this example, this is the original one. Input image, wire board, and result of processing plus 45 degrees. Plus 45 degrees. Then the line detector giving this output, and zoomed view of top left of this, zoomed view of top left of this is giving this line detection. And then zoomed view of the bottom left. See, suppose if you observe, you can find out here also and here also. Okay, I'll remove the marks, then you can identify them. See here you can see by little observation. So bottom right region zoomed one is this one, and the image with all negative values set to 0, then for that line detection is this one. Okay, and all positive values are giving this output. So in this way, by using the Laplacian and second order double line derivatives, we can detect the lines in any direction, in any axis, bottom and top. And now edge detection, line detection, point detection are covered. Now the edge detection. What is meant by edge detection? So within an image, one edge is there, this edge or this edge, in this way. Edges are also pixels, and where the brightness of the function changes abruptly. So here we use edge models. So suppose this is the example, then suppose we change the brightness um, of this pixels. Suppose we change the brightness of here, we change brightness of this one, then easily we can identify edge. So that is the process we apply the in the edge detection. So this is the original image. For this, from left to right, all these are the models, and all these are represented ideal step by step ramp. Okay, so here first edge detected and it is in a ramp. Okay, so step by step ramp detection of the roof of the edge and their corresponding intensity profile values we can identified by the edge detection models. And where we apply this, where we use that edge detection, what is the need? So here, see, this is an image actually zoomed the ramps. So in this point the ramp is zoomed here, and for this point the ramp is zoomed here, and for this point the ramp is zoomed here. Okay, so all these are the roof edge profiles. The profiles are from dark to light. So areas indicated in short line segments are showing small circles. Okay, so this area is showing by shown by this circle. This area is shown by this circle. Okay, so in this way we can identify what is there in the edge, what is there in the edge, any blocking, any disease, any, we can identify easily. Now applications and the outputs of the edge detection. Now what are the formulas behind that? So basic edge detection by using first order derivative. See here, it is a gradient function. So delta f is similar to gradient of f. Okay, which is g of x, g of y coordinates, it containing gradient of f means it is the vector of g of x, g of y, x coordinate, y coordinate, which is defined as first order, which is defined with the first order derivative, which is dou f by dou x means f with respect to x, and dou f by dou y, f with respect to y. And from this gradient function, the magnitude of delta f, we can define it as the magnitude as m of x comma y, which is the magnitude of magnitude is the method of delta f, which is the expression square root of g of x whole square plus g of y square. Okay, so the gradient function, from the gradient function we can get magnitude, and then to get the magnitude we will apply this function. To get the gradient we will apply this function, this expression. And for the direction of delta f, the direction of delta f is represented as alpha of x comma y, which is tan inverse of gx by gy. This is the direction. This expression gives the direction. Now the direction of the edge, which is phi, when it is phi, which is alpha minus 90 degrees. The direction of edge we can represent with the phi, and we can get that by the expression alpha minus 90 degrees. So this is giving the direction of edge, this is giving the direction, this is giving the magnitude, this is giving the gradient. From these basic first order derivatives for the edge detection, the edge normal, to do the edge normal we take gradient function, and to do the edge unit normal we do the calculation delta f, this edge normal, divided by magnitude of delta f, this one. And in sometimes the magnitude is approximated. To do the approximation, magnitude approximation, so to do the approximation or to do the absolute value, to get the absolute value we will apply this mod. Mod symbol gives the approximated mod value, means dou f by dou x mod plus dou f by dou y, or magnitude of delta f is equivalent to max of, means maximum of this expression. So by using this expressions we will do edge detection. So whenever you got the edge detection, those equations you have to write first order derivative, just the simple equation for the first order derivative. Now see, suppose this is the image, then this is representing the gradient is the psi, this is the psi, and this is representing the edge direction is phi, we seen, and the white color is represented with the 255 and the black color is 0. And the edge detection algorithm we can apply as, now see the edge detection applications. See, using the gradient to determine the edge strength and direction at a point. See, each square is a pixel value. This is one pixel value, this is another pixel value in the within the image, and this is the x coordinate, this is the y coordinate. Then the edge is perpendicular to the direction of the gradient. See, this is the gradient vector, and the edge is perpendicular to the gradient vector, and at that point we calculate the gradient. So to calculate the gradient we have to apply one-dimensional or two-dimensional edge detection mask. See here, this is the one-dimensional mask, and this is the for vertical and this is for horizontal. Okay, for one dimensional mask we will use this mask values, and for the 3 by 3 region of image, okay, then we will apply this mask Z1, Z2, Z3, Z4, Z5, Z6. So to compute the gradient, we will use this 3 by 3 region mask upon the image. And suppose we use Robert's edge detection algorithm, then we apply the mask values these. And suppose we are using Privet edge detection algorithm, then we will use these masks. And suppose Sobel edge detection uh, algorithm, suppose we are applying, then these are the masks we use. And from these masks, these for the 3 by 3 region, and these for the Privet and Sobel, another type of mask for edge detection in a diagonal means. So these are computing gradients for Robert and Sobel. These masks for Privet, it is calculating the diagonal edge detection, and these marks we are using in the Sobel edge detection algorithm for diagonal edges, and these are for computing gradients. And when we apply these masks upon an image, see, these are the example ones. So see here, this is the original image. Okay, so upon this original image, suppose we are applying gradient in the x direction by using the Sobel. Okay, then this is the output from original to here. And suppose we are applying the mask upon this, then this is the output. And suppose we are applying the gradient upon this, this is the output. So this is the Sobel edge detection, and this is the mask applied output, and this is the gradient applied output. And suppose we are applying in the same sequence a 5 by 5 averaging filter for smoothening, okay, then the smoothening upon Sobel is giving this output. The smoothening average in this filter resulting this on within the gradient, this is the output. The Canny edge detector, which is very important one to find out the edges, to detect the edges. The Canny edge detector, uh, within this, the optimal for step edges corrupted by white noise we are using. Step edges corrupted by white noise. We are optimizing these one. The objective of Canny edge detector is, first is the lower error rate. The edges detected must be as close as possible to the true edges. So that we can achieve low error rate, and the edges located must be as close as possible to the true edges. Then edge points should be well localized. If this is achieved, then our edge points should be well localized. So our objective is low error rate, and edge points should be well localized. And the next objective is single edge point response. How we can achieve this? The number of local maxima around the true edge should be minimum, so that we can achieve single edge point response. And for this Canny edge detector, the algorithm is we know f of x comma y is our image. So let f of x comma y denote the input image and g of x comma y denote the Gaussian function. Then we can define the Gaussian function g of x comma y is equal to, with the expression exponent of x square plus y square by 2 variance square, and we form a smoothed image f of s of x comma y. So this is the Gaussian function. From this we can form the smoothed image by convolving g and f. How we can convolve by this expression? Smoothing image f of s of x comma y is equal to g of x comma y into f of x comma y. Then the continuation process, the remaining step of the Canny edge detector is, so here the smoothing and the Gaussian function we defined. Now compute the gradient magnitude and direction. Here the direction means it is the angle. So how to compute the gradient magnitude and the direction? M of x comma y is expressed as root of gx square plus gy square. We already seen this gradient magnitude, and alpha of x comma y is equal to arctan of g of y by g of x. So from this we can get the direction angle, where g of x is dou f of s by dou x and g of y is dou f of s by dou y. Here the f of s is the smoothing function from here. So any of the filter mask pairs we can apply upon this g of x and g of y. According to that, I'll show an example, which is, one second, I'll zoom it. This is one second. I'll erase it. The combination of that and this are disabled. Now I'll zoom this. Now see this. So two possible orientation of a horizontal edge in a 3x3 neighborhood. So this is edge normal point and this is edge normal point. Two possible orientation horizontal edge neighborhoods, these two are, and this is the range of values of alpha, the direction angle of edge normal for a horizontal edge. So this is the edge, this line is the edge, and this line is the edge normal got from gradient vector, and these are the directions. And the angles range of edge normals for the normals, four types of edge directions we can see from here. This is the horizontal edge, this is the vertical edge. Okay. This is the edge directions. Now we can see the Canny edge detector method, the final operation, which is threshold. Threshold is denoted with the g of n of x comma y, and this is to reduce false edge points. What is meant by threshold? Threshold means a threshold is what you step across when you enter a room. What step you crossed to enter into a room. That step is called the threshold. more elaboratory. A threshold takes you from one place into another, and when you are about to start something new, you are also on a threshold. So, a threshold is a point of departure or a transition. So, the final operation is the threshold calculation. Hysteresis thresholding expression is g of nh is of n x comma y is equal to g of n x comma y, which is greater than or equal to t of h, and g of nl x comma y is equal to g of n x comma y, which is greater than or equal to tl, and g of nl is equal to gnl minus gnh. So by applying these expressions, now we summarizing the Candy edge detection method. First step, Candy edge detection method. First step, smooth the input image with a Gaussian filter and write down the expression here. Next, second step, compute the gradient magnitude and angle images. Write the expression of gradient magnitude and angle directions. And next step, apply non-maxima suppression to the gradient magnitude image. And finally, use double thresholding and connectivity analysis to detect and link edges. So this is the Candy edge detection method. For that, this is the example. See this. So this is the original head CT image with intensity values scaled into the range 0, 1. Then upon this, if you apply the thresholding, the threshold gradient of smoothed image is this one, threshold of smoothed image. Then the orientation using the Marr-Hildreth algorithm, this is the output. And we applying the image obtained using Canny algorithm, then this is the final output. So we can diagnose any disease, anything from this, any type of edge detections where it is something, what happened, what is the wrong, where is the wrong, in that way. Now, so in this board we have seen the topics: segmentation fundamentals, introduction, first and second order derivatives, the basic formulas, background, Laplacian background, expression, and detection of isolated points. First, we have discussed how to detect isolated points in the image, and after that, we discussed the line detection. And after that, we discussed edge detection, how to detect the isolated points from the point detection, and after the line detection, after the edge detection, a method which is Canny edge detection, which is important. These are the topics we covered within this board. For the topic segmentation, we will see the continuation of the segmentation in the next board.